Hi, Astronomy. Mr. Janowski here with the next part of the Chapter 2 slides. So, what type of model of the heavens puts the Earth at the center? That would be a geocentric. So, geo meaning Earth. So, this is an Earth centered model. And what's the other type? What type of model of the heavens puts the Sun at the center? Heliocentric. So, helio meaning sun, sun centered. So, remember that a heliocentric model had been proposed in the 3rd century BC by Aristarchus. So Aristarchus was the guy who figured out that the sun is actually much bigger than the Earth. Um, he got how much bigger pretty wrong, but he did realize that the sun was bigger. So he said, well, if the sun is the bigger thing, maybe the Earth goes around the sun and not the sun goes around the Earth. And he was right, but all of his contemporaries rejected that idea, and they had reasons to reject it. And for about the next 1500, 16, 17, 1800 years, nobody really accepted the heliocentric model, which is, correct. It is, the sun is at the center of the solar system, at least. So yeah, there was a chapter 2.1 quiz. So yeah, if you haven't taken that, take that. So the planets are things. So remember back to the celestial sphere idea. So the stars in the celestial sphere, well, they all rotate, across the sky at night, or they rotate around the north and south celestial poles. So Polaris doesn't move, but the rest of them move throughout the night. But the stars in the celestial sphere don't appear to move relative to each other. They're all kind of locked in place. So ancient cultures knew that, but they noticed that there were 5 stars, in scare quotes, that broke that rule and did seem to move. So they called those planetae, which is Greek for wanderers. So today we know that those aren't stars; they're planets. So don't confuse the idea. Of course, by now in your life, you've seen images, nice pictures taken with great telescopes or of actual probes of the planets, so you know what the planets all look like. But if you were, living in an ancient culture, you wouldn't have those pictures. You wouldn't have a telescope. So you would just see little bright points in the night sky. They look exactly like stars. Um, so, yeah, they thought those were the stars that wandered. And again, the stars on the celestial sphere don't move relative to each other, except for these. They were able to see 5 that did appear to move. So they tended, these were the ones that were wandering. So they called them the wanderers. So these are the 5 stars that are visible with the naked eye. Also, Uranus apparently sometimes is visible with the naked eye from a good viewing place, but people hadn't realized that one was moving. It's very dim, but so yeah. Mercury, Venus, Mars, Jupiter, and Saturn. So we know them by their Greco-Roman names. So modern astronomers use the ones from that part of the world, matching up with those, that mythology. Other ancient cultures, of course, who weren't Greco-Roman would have not used the Greco-Roman names. They would have matched the wandering stars to their own things, to their own mythologies. So, neat idea here. So remember we talked about the ecliptic. So the ecliptic is the plane of the Earth's orbit around the sun. So do the other stars, do they move in that same plane or do they move completely differently? Are they going at like right angles and just all going around kind of at random? The answer is they're all pretty close to the ecliptic. And this is a result of how the solar system formed. From like a giant spinning disk of matter that flattened itself out under centrifugal force. And where there were clumps in that giant spinning disk. So think of like throwing a ball of pizza dough in the air and spinning it the way they do at pizzerias sometimes. The way the whole thing flattens out into a big disk. Yeah, that's basically how the solar system was formed. And the big clump in the middle, that became the sun. And the little clumps, where there happened to be a little bit more mass out in the disk, those would gather up the rest of the mass, and those became the planets. So yeah, the planets are all basically in the same plane. It's not exactly the same plane. The other planets' orbits are, they're tilted a little bit, but it's pretty close to the same plane. So the planets are always located near the ecliptic because their planes are basically in the ecliptic. It only varies a little bit, which means they go through the signs of the zodiac. So the actual motion of each planet appears to be west to east across the ecliptic. Now, if a planet is up and visible at night, it's going to rise in the east and set in the west, just the way everything else rises in the east and sets in the west. But if you look at that planet night after night, you will notice it tends to move west to east, usually. More on the usually in a second. So yeah, this motion, this west to east motion that you see night after night, is very slow compared to the daily motion. The apparent rotation of the celestial sphere. So you can't stare at a planet and observe it moving across the sky over the course of a night. But if you take images, a few nights apart, you'll see that it moves, and it usually moves west to east. So usually, but not always, periodically, each planet will appear to temporarily reverse its motion across the sky and travel east to west for a while. When this happens, this is called retrograde motion. So yeah, here we're following Mars. So Mars, these pictures are like 5 or so days apart. So yeah, it's moving west to east across the sky. This is its normal motion. And then all of a sudden starts to slow down. So, several nights apart, it's slowing down, then it stops, and then it starts going east to west for a while. And then it slows down, it's east to west motion, and then it stops, and then it goes back to normal, west to east again, across the sky. So yeah, this is Mars, pictures taken roughly a week apart. Yeah. Then here's the Pleiades, which is a cool one. So this retrograde motion is only apparent motion. And here's why it actually happens. So in this image, we have the sun in the middle, and we're just looking at Earth's orbit. The Earth goes around this way, and also Mars's orbit. So Mars, being a little further out than Earth, it's got a bigger orbit to go around. And then for reasons we'll get into in a later chapter, the fact that Earth is closer means that it moves faster. Not only does it have a smaller orbit to make, but it's actually moving faster. So what's going to happen is the Earth, every once in a while, is going to overtake Mars. It's going to lap Mars. So think of two runners running around a track, and the one on the inner lane is running faster than the one on the outer lane. So the one on the inner lane will, periodically overtake the outer one. And that causes this apparent backwards motion of Mars against the things in the way far distance. So it's really, retrograde motion is really apparent retrograde motion. The planet itself, the planet of Mars, is not going west to east, slowing down, stopping, going the other way, slowing down, stopping, and then returning. Mars is just chugging along. So as you watch Mars go across here, take it from the top, here's Mars, just chugging along, doing its normal thing. It's only appearing to move strangely because the Earth happens to be lapping it at a certain point. Apparent retrograde motion. So this retrograde motion, all the ancient cultures, they knew about this, and it was very difficult to explain using a geocentric model with the Earth at the middle. Difficult, but they tried. They came up with all these different things. So one of these models, I want you to know this model, or the person who came up with this model by name, Eudoxus. So ancient Greek astronomer Eudoxus. So he had this model called Crystalline Spheres. So I just think this is a very lovely, poetic kind of name for this thing. It's entirely wrong. This is not at all what's happening. But it's nice to think about the heavens and the crystalline spheres and all the things rotating around. So go write a poem about that. But that ain't how astronomy actually does. So anyhow, according to Eudoxy's model, he was geocentric, so he had the Earth at the middle. And then the Earth is kind of nested in the center of all of these, ever-increasing crystalline spheres. So think of Russian nesting dolls at this point. So he had all the planets out on these giant crystalline spheres. For some reason, he thought there were these giant crystalline spheres. And the planets are going around. And the crystalline spheres are rotating around the Earth at their different rates. And you can adjust this, and he could adjust the rates at which he thought these things were spinning, and get pretty good agreement. But retrograde motion was difficult to explain using Eudoxy's model. So how he imagined it was each one of these crystalline spheres is actually kind of two crystalline spheres sandwiched against each other, and the two spheres are spinning at different rates. And using these two different spinning rates of the two crystalline spheres, he was able to kind of get it to match up with the observed retrograde motion that we saw every once in a while. So not perfectly, but kind of. So a similar model, and the historically more important model was from Ptolemy of Alexandria. So he came along after Eudoxus, like 400 or 500 years after Eudoxus. And his model involved what is called epicycles. So epi means upon or on top of, cycle means a circle. So according to Ptolemy, he would have been geocentric, so he has the Earth at the middle. So here's the Earth, and down here, here's the Earth at the middle of kind of a spinning bicycle wheel. So he had the planets going around kind of on top of this big spinning bicycle wheel. But to explain the retrograde motion, he put another spinning wheel on top of the bicycle wheel. So imagine like a spinning frisbee attached to the end of this bicycle wheel. And by inventing this circle upon the circle, so the frisbee on the edge of the bicycle wheel is the epicycle. So this is how he explained the retrograde motion. So if we're looking at this picture up here, here's how Ptolemy imagined the retrograde motion to work. So normally, the planets are going around like this, so kind of counterclockwise. But every once in a while, the motion of the inner sphere would kind of dominate, and you would get this kind of backwards loop. So this would be the retrograde motion. And then it goes back to normal for a while, and then you get another backwards loop, and so forth and so forth. So these little twists here, this is the retrograde motion. This is how Ptolemy explained it. So these are, circles upon circles. So if you adjust, these imagined circles, both the big one and the small ones, you can kind of get this to match up with the retrograde motion that you're actually observing. However, not exactly. This model couldn't work exactly. So the only way to fix it is to just keep adding more circles. So after a while, you don't have one circle on this circle. Now you have to put another smaller circle on top of this already smaller circle, and then another circle upon that. So this is circle upon circle upon circle. So he could, by doing that, you could get it to work closer and closer and be more and more accurate, but at the expense of adding much greater complexity. So this violates this idea called Occam's razor. This is a philosophical razor and a wonderful thing to have in science. So the way Occam, William of Occam, this monk, the way he said it was entities must not be unnecessarily multiplied. It is more commonly stated, Occam's razor is more commonly stated now, as all things being equal, the simplest explanation tends to be the correct one. It isn't always the correct one, but it tends to be the correct one. So if you have two competing scientific theories, and both of them explain a certain thing, but one of them is much more complex than the other one, it has all of these other features that need to be working for the model to be accurate. Well, the more complicated one is probably wrong. Go with the easier one. The easier, the simpler one will tend to be correct. So again, it doesn't prove anything. Philosophical razors don't prove things, but they do cut out, complexity, and they leave you with something simpler. So it's a good kind of guideline, but it's not, an ironclad proof of an idea. So then we talked about Islamic and Asian astronomy. So importantly, historically, what we know about what the ancient Greeks and the ancient Romans thought about astronomy and lots of other things, philosophy, math, all of that stuff, we only have their original documents because after, classical Greece and classical Rome, when, kind of Western Europe was going into, I'm simplifying it, but kind of their dark ages, that was when the Islamic cultures were rising. And so you have the Islamic Golden Age. And the Islamic scholars, around the year 800, 900, 1000, they had a tremendous appetite for gathering up books and knowledge and all this old, everything that the Romans and the Greeks had come up with. They collected all of their works. They translated them into Arabic. They thought about their ideas. They made commentaries on their ideas, and they recorded them. So in a lot of cases, the only way we know what ancient Romans and ancient Greeks actually thought was because their ideas were written down by later Islamic scholars and then translated back into Latin and things. And so that's how these things were preserved. So the effect of these ancient Islamic scholars is seen in words like zenith, which would be like a Romanization of some Arabic term. And also the fact that all of the very bright stars, the stars that are bright enough that they have their own names, like Betelgeuse, Aldebaran, and Rigel, these were originally Arabic names. So they got translated. Aldebaran probably would have been two separate words, al something or other in Arabic, and then it gets Romanized again, so it's not really original. And also in mathematics. So algebra, algorithm, these were originally Arabic terms from the Arabic or the Islamic Golden Age, and also Arabic numbers. The numbers we use, the numbers you learned when you were a little kid and are still using today, these are Arabic numbers, more properly called Hindu Arabic numbers. So if you're interested in that, I'll put a link to this SciShow, how the Arabic numbers got to the West through this guy, Muhammad ibn Musa al-Khwarizmi, who basically, he didn't really invent algebra, but he kind of codified it, wrote it all down in this book, and this book was hugely influential, and it brought all of those ideas and Arabic numbers to Western culture. So interesting stuff. Also, the ancient Asian astronomers, particularly the Chinese, they were tremendous at keeping detailed, accurate records, and that's how we know the dates of ancient eclipses, when there were ancient comets, sunspots, exploding stars, novas, things like that. So these things would have been recorded in the West, but in the West, the records are kind of all over the place, and they kind of suck. Whereas ancient Chinese astronomers kept very detailed, accurate records. And so if we want to know the date of an eclipse, in the 1st or 2nd century BC, you can figure out the exact date that eclipse happened. You can figure out the exact date that a new star appeared in the sky, because the ancient Chinese astronomers kept such accurate records. So yes, these records are still of use to astronomers today. So moving on, astronomy in the Renaissance. Polish physician, lawyer, and astronomer Nicholas Copernicus. So he began the demolition of the geocentric model. So from the ancient Greeks up until 15th, 16th century, everyone's still going with the geocentric model that has the Earth at the middle. Copernicus is the guy who really starts to undo this. So Copernicus looked at all of this old data. He looked at Ptolemy's records of planetary positions, over centuries, and all of this stuff. And he tried to make all of this stuff work with a geocentric model, but he couldn't make it work. So this led him to reconsider Aristarchus's heliocentric model. So Aristarchus, remember, he is 3rd century, 4th century BC. He's the first guy. He is our ancient heliocentric astronomer. He's the first one to put the sun at the middle of the solar system, and no one believed him for about the next 1800 years or so. But Copernicus looked at Aristarchus's old model. He was aware that Aristarchus had considered this, and then so he tried to make the stuff work using a heliocentric model based on what Aristarchus had said, and it worked. So here you see X'd out. This is Ptolemy's epicycle thing with the Earth at the middle. And this is all very complicated. And why should there be a circle with another circle on top of it, and a circle on top of that, and a circle on top of that? This is much simpler if you put the sun at the middle and the Earth going around. So in particular, retrograde motion is hugely important in figuring out these models and which one was correct, which one could explain retrograde motion more simply. So just using Occam's razor, a heliocentric model explains retrograde motion much more simply. The sun's in the middle, the Earth's going around, and the planets like Mars that are further away are going around slower. So when the Earth laps Mars, that's when you get the apparent retrograde motion. And this is a much simpler model than this very complicated epicycle one. So there's that. So I'll put a link to this too. This is just a little video explaining the retrograde motion without astrology. Astrologers love retrograde motion, or maybe they hate it, they fear it, it freaks them out. So in astrology, when a planet starts going backwards, everything goes nuts, and everyone's horoscope gets all messed up, and crazy things can happen. Of course, it's the 21st century now, and we've known for hundreds of years that astrology is just absolute nonsense with zero value to it at all. So take that, astrology. So to review, what was the key feature of Eudoxy's model to explain retrograde motion? Eudoxus was the crystalline sphere guy. So that was that. And then a few hundred years after Eudoxus, Ptolemy came along, and he explained retrograde motion using a different model. Ptolemy was the epicycle guy. So circles upon circles. That's Ptolemy's idea. And again, to be clear, both of these ideas are wrong, but that's what people believed. And especially Ptolemy's idea up until, the 15th or 16th century. Everyone liked Ptolemy's idea. So who was the ancient Greek heliocentrist? Who was the first guy to realize that, no, the sun's in the middle? That would be our buddy Aristarchus. So yeah, he did a few things. And he's the one who, by figuring out the relative sizes of the Earth, the Moon, and the Sun, realizing that the Sun is bigger than the Earth, he's the one that put the Sun at the center. And he was correct. But it took, a millennia and a half or more for people to actually accept this idea. And who was the first guy, the first modern heliocentrist? That would be my Polish buddy, Nicholas Copernicus. So that's it for this part of the slides. Hopefully you're finding this helpful.